Hello and welcome back to our journey through the standard template library in C++. Today is day 10 and we are going to take a deep dive into one of the most fundamental and widely used data structures, the stack. We will explore how it works using the LIFO principle, learn about the std: stack container adapter in STL, understand the operations it supports, and see how it leverages other containers like vectors and deques under the hood. By the end of today's session, you will not only be comfortable using stacks in code, but also understand where and why to use them effectively. Here's what on our roadmap for today. First, we will understand what a stack is conceptually, how it behaves, and where the LIFO principle comes in. Then we will explore std: stack in STL, its syntax, methods, and the containers it builds upon. We will walk through code examples, discuss time complexities, and analyze practical use cases. Toward the end, we will look at how to build a simple stack manually using vectors and deques, cover common mistakes developers make, and finally wrap it up with hands-on practice problems and your homework for the day. Let's begin. So what exactly is a stack? A stack is a linear data structure that follows the last in, first out, or LIFO order of operations. Think of it like a stack of plates in your kitchen cabinet. The last plate you put on is the first one you take out. You can't remove a plate from the bottom without removing the ones above it. Similarly, in a stack, the last element pushed in is the first one that comes out. This simplicity makes stacks powerful for managing data in a controlled, predictable way. Let's talk more about LIFO, or last in first out. Imagine you are pushing integers onto a stack in the following order: 10, 20, and 30. The last element you inserted is 30. It's now on top. When you perform a pop, 30 is removed and the new top becomes 20. So the last value pushed in is always the first to come out. This behavior is extremely useful in programming, especially in scenarios like function calls, undo operations, and parsing expressions where you need to reverse or backtrack through elements. C++ makes it easy to use stacks through its STL, the standard template library, with the std: stack class. It's defined in the stack header and is what we call a container adapter. This means that it does not store elements on its own. Instead, it adapts existing containers like deque, vector, or list. By default, it uses deque. The stack interface gives us just what we need for a LIFO structure: push, pop, top, empty, and size. Nothing more, nothing less. It's a focused tool for focused use cases. Let's look at the core functions std: stack provides. First, push adds an element to the top of the stack. Pop removes the element at the top, and note it does not return it. So you will want to call top beforehand if you need to access it. Top lets you pick at the element on top without removing it. Empty checks if the stack has no elements, and size returns how many elements are currently in the stack. These operations give us all the control we need to work within the LIFO paradigm efficiently. Here's a short code example that demonstrates stack operations. We create a stack of integers, then push two values onto it, 10 and 20. When we call top, it returns 20, the most recently added element. Then we pop the stack, removing 20, and now top returns 10. This simple sequence clearly shows how the LIFO mechanism plays out in real time. You will be using this behavior frequently in algorithms and logic-heavy applications. One interesting thing about std: stack is that it does not function alone. It wraps around another container. This is what makes it a container adapter. By default, it uses a deque because deques offer efficient insertions and deletions from both ends. However, you can also use a vector or a list if your use case demands it. For example, if you don't need frequent pops but want tight memory allocation, vector may be ideal. When performance tuning, the choice of underlying container can make a significant difference. Time to talk about performance. All core stack operations push, pop, top, empty, and size are constant time or peak of 1. This means that no matter how many elements are in the stack, each of these operations will complete in the same time. This predictability and speed are a big reason why stacks are a go-to structure in both real-time applications and algorithm design. Stacks are everywhere in the programming world. Think about the undo feature in a text editor. Every change you make is pushed onto a stack. When you hit undo, the topmost change is popped. They are also used for parsing expressions in compilers, balancing symbols like brackets and parentheses before performing depth-first search in graphs, and managing recursive calls. Understanding stacks is like having a Swiss Army knife in your algorithm toolkit. While STL gives us a ready-made stack, understanding how to build one manually depends our grasp. Here we implement the stack using a vector. The push operation becomes pushback, pop becomes popback, and top becomes back. This version behaves just like an STL stack but gives us more control and transparency, perfect for debugging, customizing, or learning purposes. Now let's do the same thing but with a Deque. The logic is almost identical, but under the hood a Deque offers more flexibility in insertion and deletion at both ends. This version might be more performant in some cases where bidirectional access is useful. Again, pushback, popback, and back mirror the standard stack operations. Knowing how to switch containers like this will help you tailor your solution to the problem at hand. Even a simple data structure like a stack can trip you up. A common mistake is trying to access the top element or pop an element when the stack is empty. This leads to undefined behavior or crashes. Always check with memory with empty first. Also remember that stack does not support iterators or random access. You can't loop through it directly or access the third element. It's strictly top-only access. Keep these limitations in mind when designing your logic. Time to get your hands dirty. Here are some problems to reinforce your understanding. Try checking if parentheses are balanced in a string, a classic stack problem. Reverse a string using a stack, perfect for mastering push and pop. Convert an infix expression to postfix. This will challenge your logic and operator handling. And try simulating an undo system with two stacks. This one's fun and practical. These exercises are designed to stretch your understanding and improve your problem-solving skills. Let's summarize what we learned today. A stack is a linear data structure based on LIFO, last in first out. The stack class in STL provides a clean interface for stack operations and relies on other containers like Deque or vector to do the heavy lifting. We explored its methods, looked at manual implementations, discussed time complexities, and saw how stacks are used in the real world, from text editors to graph traversal. Stacks may be simple, but they are profoundly useful. Here's your assignment for today. First, solve the valid parenthesis problem on LeetCode. It's a textbook example of stack application. Then implement your own stack class using both vector and Deque to really understand the internals. Finally, take some time to read about how the call stack works during recursion. This is a foundational computer science concept that connects beautifully with what we learned today. You are now equipped with the knowledge. Let's put it into action.